Okay, so we now move into the statistical inference part of the course, which is a relatively small part of the course. I'm going to cover this over 3 videos. Some textbooks, the Cambridge textbook included, stretches this out quite a long way. There's a section at the end of the, I think it's a normal distribution exercise, which is looking at the normal approximation to the binomial distribution, and then there's a couple of, sort of another exercise looking at the normal approximation to the binomial distribution in chapter 17. However, I don't think we need to place so much emphasis on that. That's really just a small stepping stone in going from a binomial distribution to being able to work out confidence intervals. So I've tried to condense this a little to focus on what are the actual important things and what are the things that you might actually need to be able to do. This first video is going to be a relatively short one. It's really just an introduction to some terminology and yeah, and offers some basics that we'll need throughout the next 2 videos. But the next 2 videos form the crux of the content. Okay, so we want to introduce this idea of populations and samples, and I guess give a sense of what this whole topic is about. So a population is a group that you want to know something about, and a sample is a group within the population that you collect the information from. So very rarely is it practical to actually collect the information about the whole population. And so this whole idea, this whole topic of statistical inference is the maths behind taking what you know about a sample and working out how well that can be inferred to the population. Okay, so that's the whole maths about what's happening here. So if we take a sample of 10 people, can we actually make inferences about a wider population of 200 people from that? Okay, and if so, how confident can we be in those inferences? Okay, so normally a sample is smaller than the population, and the only exception to that is the census. And in fact, at the time of recording this video in August 2021, there is a census imminent. So in a census, the entire population is surveyed, so the sample is the population. But other than that, generally speaking, we're sampling from a larger population. So as I said, collecting data from a population is often not practical. It may just be that the population is too large, like the population of a whole country, which is why we only do a census every, I should have researched this before now, I don't know, I think maybe 5 years or something we do censuses. 2021, maybe that's a weird year to be 5 years. Anyway, I'm not sure what the frequency is, but it's not that often. And that's because it's quite a significant undertaking. So if the population is too large, it's often just not practical to survey or to get information from the whole population. For example, all Year 12 students in Australia. Now, realistically, that's probably not that difficult a population to retrieve information from, given that they all go to schools and we could do that through schools. But thinking about that idea that often the size of the population is the hindrance. Another reason might be that the population could be hard to access. So, for example, all of the blue whales in the Pacific Ocean. We would have, no way to be sure that we've captured every single blue whale in the Pacific Ocean. So we would always be sampling from the wider population by looking at what's happening with some of the blue whales. And the third reason is that the data process could be destructive. So, for example, if we want to test the battery life of batteries, if we were to test every battery to see how long it lasts, then we're left with no batteries. So that would always be a sampling thing. Okay, so the number of members in the sample is called the sample size, and we use lowercase n to refer to that. And the number of members in the population is called the population size, and it's referred to as uppercase N. When we're talking about a property of a population, we call that a parameter. So a parameter is a characteristic of the population, whereas in the sample it would be referred to as a statistic. So if we wanted to work out the average of something, if it's for the population, that's a population parameter. But if it's from the sample, that would be a sample statistic. Okay. So we talk about the population proportion, and that is P. And it is the number of people in the population with the desired attribute that we're looking at, divided by the population size. Okay, so that'll be the proportion of people in the population that have this desired attribute. In the sample, that would be called the sample proportion, and the notation we would use for that would be p hat. So p hat is the number of people in the sample with the attribute divided by the sample size. And really the whole thing that we're going to be looking at over the course of this topic is how do we use the sample proportion to make inferences about the population proportion. Okay, so a sample statistic will always be known exactly because we can calculate that from our sample, but due to the limitations above, we might not be able to calculate the population parameter exactly. And so population parameters are often estimated from sample statistics, and that's what we want to be able to look at. Okay, and this topic is about using a sample or many samples to make inference about the population. All right, so here's a little graphic. We've got our population. It's bigger. Its size is n, uppercase N, and the population proportion. So let's say the people highlighted in pink are the people with the attribute that we're interested in, be that number of people out of the total number of people in the population. That would give us the population proportion. Whereas we might take a random selection of just 6 people, and so our sample size lowercase n is 6, and our statistic p hat in this case would be 1 out of 6. Okay. All right, so obviously we need to think about this idea of taking a sample, and it's really important that we have this understanding that the sample must be random in order to be, well, not always, but there must be an element of randomness in the selection of the sample to ensure that it's going to give a good approximation, estimation for the population. So a good sample should be representative of the population, and there are many methods for selecting samples, but the general principle underlying the method should be to ensure that no subgroupings are disproportionately favoured or disfavoured. Okay, so the way we collect the sample shouldn't ensure, for example, that people in a particular postcode are more likely to be selected. It shouldn't ensure that women are more likely to be selected, whatever it might be. Okay, so it should ensure that every subgroup is able to be selected in equal, they're equally likely to be selected. And so one way to do this is to choose a sample completely at random, which means that every member of the population must have an equal chance of being selected. Okay, so therefore, something like standing on a street corner and surveying people there, that if you're trying to make inferences about the population of Australia and you're standing on a street corner in Melbourne, that doesn't ensure that every member of the population of Australia is equally likely to be part of the sample. So that would be a problematic sampling method. However, sometimes just a simple random sample, just randomly selecting from the entire population, is not ideal either. So if we wish to make a valid conclusion about the population from a sample, we need the sample to be chosen so that it is representative of the population as a whole, which means that different and relevant subgroups should appear in the same proportions in the sample as they do in the population. The key thing, you could get yourself caught up in knots in trying to make sure that every possible subgroup is represented. So the key really is relevant subgroups. So for example, if you're surveying a population on something where it's thought that men and women could have quite differing opinions, then it would be important that the random sample has men and women represented in the proportions that they're represented in the wider population. Okay, so the males and females themselves would be randomly selected, but you would ensure that there is a certain number of males in the sample and a certain number of females in the sample, and that's called a stratified random sample. And you might want to do that via other groupings. You might want to do that via ethnic mix, for example. You might want to ensure that the divisions of the ethnicities in your sample are representative of the population, or whatever it might be. Okay, so one way to select a random sample is to allocate a number to each member of the population and then use technology to randomly generate a list of numbers to select the sample. So let's just have a quick look at how we can use our CAS to generate random integers. So an integer being a whole number, obviously. So with our CAS, if we wanted to generate 3 random integers between 1 and 10, we would use menu, 4 for, sorry, that shouldn't be 4. I've got those numbers around the wrong way, I think. It definitely shouldn't be calculus. Let me see. No. Okay, sorry. That's completely garbage there. Let's try that again. Menu, I think we want 6 for statistics. And then we're going to want... Oh, no, sorry, 5 for probability. I think I've just got that 5, 4 around the wrong way. Let me go back. So menu, 5 for probability, 4 for random. Yeah, so they should be around the other way. Menu, 5, 4. And then 2 for integer. So random integers, and if I want to generate integers between 1 and 10 inclusive, I will put 1, 10. So if I wanted it to be between 1 and 10 not inclusive, I'd need to put 2, 9. So it will always be inclusive of those end values. And then comma, how many integers do I want to generate? I want to generate 3. Okay, I'm going to press enter here and we're going to get a couple of problems. So you'll notice that I've generated, it's meant to be a random number generator, and I've generated exactly the same 3 sets of numbers that were generated in the screenshot when I produced this document. And you would have found if you just did this as well with your CAS, for the vast majority of you, you would also have generated that exact same set of integers. So it's not very random, is it? The other problem is that we see we've got a double up. So we've generated 10, 10, and 2. Okay, and if this was trying to select 3 people from the group of 10, that wouldn't help us. So there's a couple of ways you could do it. You could either actually decide you're just going to randomly generate one integer at a time and keep generating integers until you've got 3 different ones, or I could just generate another set of 3 integers until I get a set that's got 3 different ones. Okay, so again, you see my next one is the same as what it shows in the screenshot. So one of the problems we have here is no technology can be genuinely random. Okay, it has a sort of algorithm by which it can generate random numbers, but it has to have a starting point, and we call that the seed value. And the problem is that in the factory settings of the CAS, everyone's CAS has the same seed value, and I think it's probably just 0. So what we need to do is we all need to seed our CASs so they have a different starting point. And it doesn't matter what number we choose. It doesn't have to be a single digit number. You can choose any number. Okay, so we all need to seed our CAS, okay, which means we're going to go to menu, 5 for probability, 4 for random, and we're going to go to 6 seed. And we're going to type a number, okay. One way to ensure that we would all get different numbers would be to type in our mobile phone number. Now I'm not going to type my mobile phone number in on YouTube. I'm just going to press the buttons randomly. I'm going to press enter, and now I've seeded my CAS with something different, okay. And so now if I generate a set of random integers, and if you've done the same with your CAS, so if I go to menu 5, 4, 2, and I generate 3 numbers between 1 and 10, so I could just copy down my previous entry for that, I now get a different set of integers. And you'll see this time it's different to the ones that I got on the screenshot on the handout, and that's because I used a different seed value. Again, I've got a double up, so I'm going to generate again. Okay, now 254, I've got 3 unique integers for my sample. Okay, so let's have a quick look at an example. So consider a small country school of 20 students who are having a debate over changing their school uniform. The 20 students are listed below as whether they are male or female. And look, I understand that binary distinction is problematic in this day and age, and there's a huge amount of things in maths textbooks that are problematic. It makes for a neat probability example to have a category that has 2 categories, although now it doesn't. I also apologise for the gender stereotyping of the blue and the pink, but there we are. So diagram indicates whether they're male or female and whether they are for or against the uniform change. Okay, so in order to make selecting random samples easier, the 20 students have been numbered so that we can randomly generate a number to select our sample. Okay, part A, calculate the population proportion, P, for those who are for the uniform change. Okay, population proportion is out of our total population of 20 students. What proportion of them are for the uniform change? So we need to count up how many are for. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 10 out of the 20 students are for the population change. So that's a population proportion of 0.5 or half. Okay, we want to use part B, use a random number generator to generate a simple random sample of 5 students. Simple random sample being every student equally likely to be selected. Calculate the sample proportion for those who are for the uniform change. Okay, so we're all going to get a different sample here, and that's sort of the point. In fact, in reality, we would want to generate lots and lots of samples of 5, and then look at what's happening from there. We'll talk more about that as we go down the track. So I'm going to do menu 5, 4, 2, and I'm going to generate random integers from 1 to 20 this time, and I'm going to generate 5 of them. Good, I've got a set with no repeats, straight up. Okay, so my sample, I'm going to highlight the ones that came up in my sample. 4, which is Penny, 13, which is Chris, 10, which is Greg, 11, which is Oliver, and 16, which is Tom. Okay, so there's my 5. And so I want to calculate P hat, the sample proportion for those who are for the uniform change. So out of my sample of 5 students, How many of them are 4? 2. 2 out of 5, so 2/5 or 0.4. So in this case, my sample proportion isn't too far off the population proportion. But you can see that it would be perfectly possible to generate a sample that has no people for the uniform change, or one, or all 5 of them for the uniform change. And this is where samples become problematic, and this is why actually the technique needs to be that we generate lots of samples and calculate the sample proportion. So as I said, we'll talk about that further down the track. Part C, if we were to use a stratified random sample, find the number of females and the number of males that should be selected in the sample of 5 in order to ensure that it is representative of the population. Okay, so we can see here, because the sample's been set up so that it's grouped nicely, we've got 8 females and therefore 12 males in our sample. So that means that we need the proportion of males. So males make up 12 out of 20 of the population, and so then as a sample of 5, that needs to be 3 out of our 5 are going to be males, and then females. Well, there's 8 out of 20. I mean, we could just say that it has to be 2. So that fraction of our sample of 5 means we need 2 females. So we need our sample to actually comprise 3 males and 2 females. Use a random number generator to select a stratified sample of 5 students and calculate sample proportion of those who are for the uniform change. Okay, so this time we want a stratified random sample. I've sorted it out nicely so that numbers 1 to 8 are our females, and of those we want to choose 2. So let's do our random number generator. So from numbers 1 to 8, we want to choose 2. Okay, I've got 2 different ones there. I've got person 5, who is Lisa, and person 8, who is Jessica. And then I want to, from the males, which are numbered 9 to 20, I want to choose 3. Okay, and again I've got 3 different ones, which is good. So 16, 17 and 19. Okay, so we've got Tom, Dennis and Neil. Okay, so we want to know the proportion that are for the uniform change. So this time I've got 1, 2, 3 of them that are for the uniform change. Okay, so P hat is going to be 3 out of 5, which is 0.6. So again, not far off the population proportion. In fact, it's impossible to get 0.5 in this sample because we've got a sample of 5 people. So, as I said, it's unlikely that we all obtained the same results in this question, and it's also unlikely that we all obtained the same sample proportions, that they're in line with the population proportion. So, as I said, the next thing that we want to be able to look at is to consider the sample proportion as a random variable, and to look at taking lots of samples and look at the probability of getting the population proportion within the sample. So we'll be looking at that in the next video. The next exercise is exercise 17A, and I've kept these questions here to have as a discussion point, although in this video recording it doesn't work as a discussion point, so perhaps we'll do that together in class. But it's worth having a look through these questions. We might just have a look at a couple of them. It's about whether the sampling method is an appropriate method. Okay, and there's no perfect responses here, but it's really just getting you to think about what are some of the limitations of that as a chosen method. So question 1, in order to determine the sort of film in which to invest his money, a producer waits outside a theatre and asks people as they leave whether they prefer comedy, drama, horror or science fiction. Do you think this is an appropriate way of selecting a random sample of moviegoers? Explain your answer. Okay, so my instincts suggest that this isn't, because if he's standing outside a theatre as people leave, if they've just left a comedy movie, they're probably very likely to say that they prefer comedy. And that might not be representative of all theatre goers, because if you then stood outside a horror movie next, they're all going to say that they prefer horror movies. So it's pretty limited. It does say selecting a random sample of moviegoers, so the fact that they're all already moviegoers perhaps isn't problematic if we want a sample of moviegoers. But there's also the issue that he's actually at the cinema, and perhaps it's the people outside of the cinema who aren't at the cinema that you want to be able to bring in, and so you want to look at why aren't they going to the cinema, what isn't represented there, what do they want to see in the cinema. So a couple of issues there. Question 2. A market researcher wishes to find out how people spend their leisure time. She positions herself in a shopping mall and asks shoppers as they pass to fill out a short questionnaire. Do you think this sample will be representative of the general population? And again, she's gone to the shopping centre, so inherently she's capturing a group of people who like to spend their leisure time shopping. And so therefore it's perhaps not representative of the people that aren't in the shopping centre. They're out on a hike, or they're at the beach, or they're at a football game, or whatever it might be. So it would need to be more wide-ranging. Part B, how would you suggest the sample would be chosen? I would say that the answer to this is almost always allocate each member of the population with a number and use a random number generator to generate the sample. Question 3, to investigate people's attitudes to control of gun ownership, a television station conducts a phone-in poll where people are asked to telephone one number if they're in favour of tighter gun control and another if they're against. Is this an appropriate method of choosing a random sample? Give reasons for your answer. Okay, so I would say that this is even less relevant now than it is at the time of writing this question, because I think the proportion of people that genuinely watch live television and therefore would be able to phone in on a poll is actually pretty small these days, with streaming and with the ability to record and watch on delay. And in fact, you're inherently probably generating quite a narrow sample of people, and that's perhaps older people who don't do streaming or don't watch their television on delay as much, and they do tend to still watch live television, and so therefore you're probably narrowing the proportion of the population that you're capturing through this method. Okay, and the other thing I think from memory, I think it says in the answers in the textbook here is something about you're also the phone-in method perhaps is not preferred by everyone, so you're sort of perhaps giving a wider variety of options by which people could engage with the poll. So these days, probably text messaging would be the better way to go, or an online poll or something maybe, or at least having the options of both or more than one way to take part in the poll could also capture a wider range of people. Question 4, a researcher wishes to select 5 guinea pigs at random from a large cage containing 20 guinea pigs. In order to select her sample, she reaches into the cage and gently pulls out 5 guinea pigs. Do you think this sample will be representative of the general population? Now, this one's a slightly funny one. I think I remember the answers in the back of the book here tend to refer to the temperament of the guinea pigs, in that she's probably more likely to be able to get easily the guinea pigs that are fairly docile and friendly, whereas the ones that are a bit fearful or a bit likely to bite or whatever, they're not the ones she's likely to pick up, and so perhaps she's getting inherently incidentally a sample of guinea pigs that have a quite calm and friendly temperament, and perhaps that might be problematic for her whatever she's going to be researching with them. So again, how would you suggest the sample could be chosen? Allocate each guinea pig a number, randomly generate the numbers, and take those guinea pigs. Question 5, in order to estimate how much money young people spend on takeaway food, a questionnaire is sent to several schools, randomly chosen from a list of all schools in the state, to be given to a random selection of students in the school. Is this an appropriate method of choosing a random sample? Give reasons for your answer. Okay, so one of the big assumptions here is that all young people are attending school, which I think is the main issue here potentially, particularly given that you're not surveying something that's relevant to education or whatever. So yeah, I think a way that captures the young people that perhaps aren't at school as well as those that are would probably be a better way of going about it. Okay, so the exercise here is actually from the textbook. It's the populations and samples exercise. I think, I can't remember what the number is off the top of my head, but I've replicated it here in Appendix C of your workbook so that you can actually write on it and reference it. I think it might be, with the textbook, I actually think the printout might be available sort of online with the login for this particular exercise. Okay,